Okay, so in this video we're going to be looking at day 3 of implicit differentiation. And our first example wants us to find all of the points where y to the 4th plus 2 equals 2y squared plus x squared has a vertical or horizontal tangent line. So just thinking about what we know about vertical lines, we know that that's going to be where the slope is undefined, because vertical lines have a slope that is undefined. And for horizontal lines, we know that we're looking for where the slope would be equal to 0. So since we're looking for horizontal or vertical tangent lines, for vertical tangent lines, we're going to be looking for where our derivative dy dx is undefined. And for horizontal tangent lines, we're going to be looking for where our derivative, our rate of change of y with respect to x, is equal to 0. Which means that to start, we're going to have to figure out what dy dx is. So I'm going to start by differentiating this whole thing with respect to x. So for my first term, I have y to the 4th. The derivative of y to the 4th will be 4y to the 3rd times the derivative of y with respect to x. Plus the derivative of 2 is 0. When we take the derivative of the right side, we have 2 times y squared. So when we differentiate that with respect to x, we're going to get 4y times the derivative of y with respect to x. Plus the derivative of x squared with respect to x will just be 2x. So now to solve for dy dx, we're going to move this 4y dy dx over to this side so that we have all of our dy dx's on the same side. If I subtract 4y dy dx from both sides, then I'm going to have 4y cubed dy dx minus 4y dy dx is equal to 2x. So now I have my dy dx on the same side. My next step would be to factor that out. So if I factor out a dy dx, then I have, not equals, then I have, back a little, 4y cubed minus 4y, and that's still equal to 2x. So then finally, to finish solving for dy dx, I would need to divide both sides by 4y cubed minus 4y. So then I get dy dx is equal to 2x divided by 4y cubed minus 4y. And since every term in the numerator and denominator is divisible by 2, we can go ahead and reduce that just a little bit, make our numbers a little bit smaller and easier to work with. So we have x divided by 2y cubed minus 2y as dy dx. So now that we have our rate of change of y with respect to x, we can use that to start looking at where we have vertical or horizontal tangent lines. So I'm going to start with the vertical tangent lines. And we said that that's where the derivative is going to be undefined. Well, in order for this to be undefined, then our denominator, 2y cubed minus 2y, would have to be equal to 0. So for my vertical tangent lines, I need to figure out where the denominator, 2y cubed minus 2y, would be equal to 0, because where the denominator is equal to 0, this is going to be undefined. So I do have a greatest common factor. Not only can I factor out a 2 from both terms, but I could also factor out a y from both terms. So I have 2y times y squared minus 1 equals 0. So then that means that either 2y is equal to 0 or y squared minus 1 is equal to 0. If 2y is equal to 0, then y is 0. And if y squared minus 1 is equal to 0, then y squared would be equal to 1. So y could be both positive or negative 1 if we were to take the square root of both sides. So we actually have 3 possible values of y that could all cause this denominator to equal 0, and therefore our derivative to be undefined. So notice though it said we need the points where we have a vertical tangent line. So I've got my y values, I need my x values now. And so to get those, I'm going to have to go back to my original equation. So we'll start with at y equals to 0. If y is 0, then I have 0 to the 4th, 0, plus 2 is 2, equals 2 times 0 squared. Well, 2 times 0 squared would just be 0. So I would just have 0 plus x squared, or x squared. And then from there, I would just have to take the square root of both sides. So I get that x is equal to plus or minus the square root of 2. So at y equals 0, we actually have 2 points on our graph where y would be equal to 0. We have one at the positive square root of 2, so x would be square root of 2, y would be 0. We also have one where x is negative square root of 2, and y would be 0. So 2 points where we could have vertical tangent lines so far. But we also have vertical tangent lines at y equals plus or minus 1. So I also have to plug those in. So let's look at where y is equal to 1 now. If y is equal to 1, then I have y to the 4th power is 1 plus 2 equals 2 times y squared, so 2 times 1 squared would be 2 plus x squared. So then I have, 3 equals 2 plus x squared. If I subtract 2 from both sides, then I get 1 equals x squared. And so I have x equals plus or minus 1. I take the square root of both sides again. So if y is 1, again, we have 2 possible values of x. So we could have y or x equal to positive 1 and y equal to positive 1. We could also have x equal to negative 1, and y would also be positive 1. So 2 more points there. Now notice what happens at my third possible value of y. If I plug negative 1 in for y, then I'm basically going to get back to this same equation, because if I raise negative 1 to the power of 4, I'm going to get 1. And if I square negative 1, I'm also going to get 1. So this is really true whether y is positive or negative 1. So if y is negative 1, again, I would have 2 possible values of x, plus or minus 1. So I could have x equal to positive 1 and y equal to negative 1. Or I could have x equal to negative 1 and y equal to negative 1. So there are 4 more points based on y being plus or minus 1. So all in total, we have 6 different points on the graph of y to the 4th plus 2 equals 2y squared plus x squared, where we would have a vertical tangent line or a slope that is undefined. So now we need to look at our horizontal tangent lines. And we said that a horizontal tangent line would happen if the derivative is equal to 0. Well, if we look at our derivative, the only way we could have this fraction being equal to 0 is if its numerator is equal to 0. So for the horizontal tangent lines, the only way that could happen is at the points where x is equal to 0, because that would make that 0. So now let's find our y values, and again, to find the points on the graph, we need to go back to our original equation. So I'm going to put 0 in for x now and figure out what values I could have for y. So I would have, let's see, y to the 4th plus 2 equals 2y squared plus 0 squared would be 0. So if I set this equal to 0, I have y to the 4th minus 2y squared plus 2 is equal to 0. And at first glance, you might think that this is a difficult problem to solve because you have a power of 4. But notice that my middle term is y squared. So really, I could treat this like a quadratic, because this is y squared squared, this is y squared, and that would be 2. If you're not seeing that, maybe come over here to this side and play with it a little bit. Let b equal y squared. And if we rewrite our equation with that, I would have y squared squared, so that would be b squared, minus 2 times y squared would be 2b, plus 2 equals 0. And if we write it that way, it's a little bit easier to see that that's going to be a quadratic. And I can quickly tell that I'm not going to be able to factor this because there are no factors of 2 that are going to add to give me negative 2. So I'm thinking probably the easiest way to approach this is going to be using the quadratic formula. So b would be equal to negative b, so negative 2 plus or minus the square root of b squared, so negative 2 squared would be 4, minus 4 times a is 1 times c is 2, divided by 2 times a is 1. So b would be 2 plus or minus the square root of 4 minus 2 times 4 is 8 over 2. And at this point, we start to notice a problem, because if I try to simplify this any further, I have 2 plus or minus the square root of negative 4 divided by 2, which means that this, because my discriminant here is negative, is going to give me non-real solutions. So in other words, if x is 0, we are not going to get a real value of y. So theoretically, our derivative would have a value of 0 if x is 0. But because of the way our equation is defined, there are no values of y that can make that true. So we don't have any points. We have a possibility of an x value of 0, but if we put 0 in for x, we don't get any real solutions, which means that there are no points on this graph where we could have a horizontal tangent line. So 6 possible points with a vertical tangent line, no points with a horizontal tangent line. Okay, so let's go ahead and move on to our next problem. This one's a little bit different because if you'll notice, it says that they want us to differentiate the equation x squared minus y squared equals 1 with respect to the variable t and express dy dt in terms of dx dt. So we kind of talked about this idea just a little bit before. We don't always have to differentiate with respect to x. Sometimes we're not looking at how y changes with respect to x. Sometimes we might be looking at how y and x change simultaneously with respect to some other variable, like, for example, time. And so that's kind of what this problem is asking us to do. Adjust this real quick. Oh, there we go. There we go. All right. So we're going to differentiate x squared minus y squared equals 1 with respect to t. And we're going to solve for dy dt expressed in terms of dx dt. So this time, because I'm looking for dy dt, I'm going to start by taking my equation, x squared minus y squared equals 1. And this time, I'm looking for the rate of change of y with respect to t. So I'm going to differentiate with respect to t. So here we go. I have x squared, and the derivative of something squared is going to give me 2 times that something to the first power times the derivative of that thing with respect now to t. And for my next term, minus, again, I've got something squared. The derivative of something squared is 2 times that thing to the power of 1 times the derivative of that thing, y, with respect to t. And that's going to be equal to the derivative of a constant. The rate of change of a constant will always be 0. It doesn't change. That's why it's constant. So now I need to solve this for dy dt. So if I want dy dt, I'm going to start by isolating that. I'm going to subtract the 2x times dx dt from both sides. So negative 2y times dy dt is equal to negative 2x times dx dt. And so if I divide both sides by negative 2y, and those cancel, and I have that dy dt then will be equal to, well, let's see, those would cancel as well. So I'd have x divided by y times dy dt. So in this case, if I wanted to know the rate of change of y with respect to t, really I need to know about 3 different things. I need to know something about x, I need to know something about y at that particular instant, but I'd also need to, oh, that's typo. I misspelled x here. That's dx dt. I'd also need to know something about how x is changing with respect to t. So now it's dependent on those 3 things. What is x? What is y? But also, do we know anything about how x is changing with respect to t? And if we know that information, then we could actually discuss a little bit further how our y value is also changing with respect to t. For now, we'll leave it like this since we don't have any further information.